just to introduce myself, my name's Nichola Roberts, and I'm a technical lead of NLP. I'm a data scientist, and I've worked at Connex for about 2 years. So just in case you didn't know, NLP stands for natural language processing, and NLP has really been hitting the headlines in AI recently. So I'd say NLP is probably one of the most exciting and rapidly growing areas of data science and AI right now. I might be a little bit biased, but I think that's probably true. So there's been groundbreaking models been released one after the other recently. And these large language models are very good at generating human language pretty much at a level indistinguishable from humans at the moment. And this is based on developments in neural network architecture. So the invention of transformers and attention mechanisms. So just to go through some of the different models that have been released. So DALL-E was released in January 2021, and that can generate images from text prompts. And then we have ChatGPT that was released November last year. That can pretty much generate any text that you want based on a input prompt. So it can generate poems or computer code, which is very good at explaining the answer to any question that you ask it. And then most recently, GPT-4 was released March this year, so just last month. And so these large language models, they're very good at a lot of different tasks. So they're very good at pretty much anything but translation, question answering, text summarization, or even creative writing. So we're going to have a look at a bit more in depth in the latest model. So this is GPT-4 that was released last month, which is an update to ChatGPT. So this was trained on a huge amount of training data. OpenAI, who make the model, haven't given away any information about their training data, their training method, or their neural network architecture. But a lot of news articles have speculated that the model has about 1 trillion different parameters that have been trained. So this model was trained on a lot of data from probably a lot of different things, probably across the internet. And then it was fine-tuned based on human annotators that were saying which responses that they preferred. So we trained using reinforcement learning to change it from a language prediction model to more of a chatbot, more of a question answering type model. So GPT-4 is very good at performing a lot of different tasks. So for instance, in this graph, it shows how well GPT-4 performs on some different exam papers compared to humans. So on the y-axis, you can see the percentile compared to humans. So it shows you what percentage of humans GPT-4 perform better than. So if we look at some of the test papers, so the first one on the left, so we've got stat reading and writing, which is an English comprehension test. So GPT-4 has performed better than 95% of human test takers. So this is understanding language, not just on a surface level, but on a much more in-depth level. Then we can see some different exams. So stat maths is performed better than 90% of human test takers, which is impressive because I think ChatGPT has been is famous for not being very good at doing maths, but obviously they've improved this for GPT-4. Then we can see some different exam papers. We've got AP Calculus, which is Advanced High School Calculus, which is not something you would expect a large language model to be good at, but it's performing better than 45% of human test takers. So the question is, now we've got these big large language models like GPT-4, does that mean that all NLP tasks are now solved? Does that mean that NLP jobs like mine are redundant and all we need to do is make text prompts and GPT-4 can provide the answer to everything? But luckily for me and my job security, the answer is no. They are very well performing models, but they're also very computationally expensive. To train these models from scratch, they cost millions of pounds. To even just get predictions from them, they're going to need a lot of computational power, GPUs, a lot of processing power, a lot of memory, and just not really feasible, and definitely does not scale. So we have a lot of concurrent calls across different agents, different clients at Connex, and we're not going to be able to use these kind of models in that situation. The other problem is that to run them, they're behind external APIs. So we have to send our client data and our client's customer data through to an external company, which is a security risk, sending the client secrets and perhaps personal information, breaking GDPR. And then the final reason the models might not be the best is that they might not have any domain-specific knowledge. So these models are very good at understanding language in general, but they might not understand specific things for our clients. They might not understand the structure of our clients' sales calls. So where does that leave commercial businesses like Connex One? So we've got actually a lot of other options available to us. So not everything needs billions of parameters. Sometimes a small model is good enough. So there's a lot of advantages to these small models. They're faster to predict and they're faster to train. So you can train a model in like a fraction of a second. You can probably get thousands of predictions back in a fraction of a second. And this is good because it's a lower cost to the business and therefore to our clients. You need like less computational power. That means it's also very scalable. So it can handle all the calls that we deal with at Connex. And then the other benefit, there's no external API, so no security risk. And these models actually can do very well at a lot of different tasks. So recently, I had to label times in a call when agents ask specific questions. And because agents had very little variation in how they asked the question, a very simple model based on only a few, like 25 training examples, actually performed very, very well and adequately. But there is a problem with these models that they don't understand context very well. They won't be able to understand unseen words. They might not be able to understand unseen domains very well. So we can have a scale. We can move from the smaller models, get a little bit more complicated, to some larger models. So these are models that can understand meaning and context. And some examples of these are the large language models we mentioned before, but some of the smaller versions like GPT-2 that was released in 2019. And these have been fine-tuned maybe on more specific data. So you could have a GPT-2 that's been trained to do sentiment analysis based on Twitter data or question answering. And a lot of these models are available on the internet. So there's 180,000 models just available on Hugging Face. So the benefits to these models, there's no external API compared to like GPT-4. So that means we can use client data on them. But compared to this smaller models, they're much slower to train, much slower to predict, so therefore the more cost to the business, more money, more cost passed on to our clients. And they are less scalable than the smaller models. And then back to the original models like GPT-4. So like I said, they are too big to run locally, even if we could. They're very expensive, so just running one model on a call could cost 6 cents. So imagine all the different models that we run on all the different calls, costs can mount up quite fast, and that would be passed on to our clients. And then, like I said before, the big problem that we don't want to send our clients' data over an external API. But there may be sometimes we could use these models still at Connex, so maybe if we wanted to run one thing for our clients, for example, if they want to have a customization on the website or something, we could get GPT-4 to come up with the customized code. There are still opportunities to use these kind of models. So what kind of models do we have at Connex? So start with the most simple model we've got. We've got sentiment analysis, very standard method in NLP. So sentiment analysis determines the whether text is positive or negative. And you can imagine there's a lot of uses for this in a call center. So a manager might be able to identify negative calls, might be able to see angry customers or complaints very easily, or if a customer calls back. I lost my, okay. So sorry, carry on. So as Connex sentiment is tracked on for each sentiment of each utterance of a call. And like I said before, training data is very important in data science. And in NLP, I'd say training data never comes easily. So maybe in more typical data science, you might have a tabular data. You might have a shortage of data points. You might not have enough data to make a good model, but that's typically not the case in NLP. So we have, like everyone said, millions of call transcripts. We've got a lot of training data. The problem is that it's not necessarily labeled. So we want to do sentiment analysis. We need to have the sentiment labelled for those utterances to train our model. And luckily at Connex, we've got an internal labelling team, and they've labelled 80,000 different utterances, which is used to train our model. So though we've got a very simple model, it's actually performing very well. And I would say if we do want to improve the performance of the model, probably what we need to do is label more data rather than move to a more sophisticated model, so that our more data can handle different domains, a lot of different types of utterances. So we move on to another model we've got at Connex, and again, another quite a simple model, which is entity recognition. So this will tag entities within calls. So the entities it might tag as company names, company products, or money, and we can see that there are probably quite a lot of uses for this. So if you want to track mentions of competitors over time, or if you want to track which products are selling at what kind of cost, it's very useful for that. But you can see there's quite a lot of challenges. For example, company names can be quite unique, it might be hard to identify. And then we've taken our entity recognition and used it to mask personal information. So we found things like names, addresses, date of births, and phone numbers for the customers. And then we've used entity recognition to mask these so that they better comply with GDPR. And this is quite a challenging piece of work again, because obviously we want high accuracy. We don't want to be masking too much, but we want to be finding every example that we can. It's also challenging because speech is often interspersed. So by this I mean the agent might ask, what is your phone number? And then the customer might reply 07, the agent then repeats 07. So you can imagine it's quite a hard thing to identify. And then another example, we've got a slightly more complicated example. So this one is a neural network, but still quite a small and simple, scalable neural network. So this is an AI-based call center coach, which tracks the progress of a call in real time and detects key opportunities for an agent to improve call outcomes. So some of the examples of the call outcomes we can improve, so find a way to upsell products. So you can see in this example on the left, we've got a customer that has agreed to a certain deal, and the agent coach has realized this is a good opportunity to suggest an upgrade to the Plus package, which the agent then does. Another example, it could be overcome customer objections. So the coach could hear a customer saying that the deal is too expensive and suggest a prompt to the agent to recommend a special offer. Or another example, the coach could tell the agent to reply appropriately to customer emotions. For example, if a customer is angry, it can tell the agent to spend some time trying to validate or alleviate that customer emotion. And then the final model I'm going to talk about today is call summarization, which was one of our more complicated models that we've got Connex. So this will take the call transcript and summarize it into a paragraph. So we have lots of different call lengths. We have calls up to an hour long, so we can see the benefit in summarizing them to an hour. So the benefits are we have very quick access to the content of a call, like from a manager, or if a customer calls back, we can see past conversations very easily. The agent can understand what kind of journey that customer's been on. So for this model, we've taken one of those fine-tuned large language models that has been fine-tuned on summarization, and then we've fine-tuned it again on our own internal data. So our internal transcription team have written 3,600 summaries, which are in the format that we would like, and we've used this to train our model. So there's many different challenges in this piece of work, you can imagine. So one of the challenges is that coming up with these summaries takes about 20 seconds per call. And one of the problems with large language models is that they can hallucinate data. So we might have a lot of things in our training data, but won't be specific to that call, but it can come up with it for that summary. So ideally, we would like the agents to validate each summary, but we don't want an agent waiting 20 seconds for the summary to appear. So that's a particular challenge. Another challenge is that the call lengths can be much longer than the input lengths for the models. So models typically can have an input of 1,024 tokens, which is around 1,024 words, but our calls can be like over an hour long. We can have 4,000 tokens. This means we might do some different pre-processing. So we might have to do some extractive summarization to find the most important utterances that then we can then put in to the summarization techniques to come up with a paragraph summary. But we can imagine that will add time onto the computation. So there's quite a lot of challenges with this task, but it's one of the most, I think, interesting tasks we're doing at Connex. So to summarize, the best performing NLP models give human level performance like GPT-4, but there is still a need for much smaller, simpler models. And then the benefits of this, that there's much faster predictions, there's lower costs, and they're much more scalable, but they will have a lower performance. So deciding which model to use, what model's best, is a trade-off between performance and probably the other things like scalability, computational speed. So thank you everyone for listening to my presentation. Yeah, thank you.